Welcome to EDU World Space.
Our goal here is to compare the ground state energy and the radius of the first orbit in a Bohr model, but using gravity to hold the atom together instead of the electrical force. And the key to this is to kind of understand or look at the two relationships that give you the magnitude of the force of gravity and the electrical force. So the electrical force in the hydrogen atom goes as the electrical constant times the charge, fundamental charge unit squared over separation squared between the two charges. Force of gravity looks very similar. It is a inverse square law, but we see that the constant in the numerator is different than, of course, the electrical constant. So our goal is to take a look at the formulae for the energy levels in the hydrogen atom. And simply, wherever we see the electrical constant, we will replace it with the gravitational constant. But furthermore, we can see how the relationship will be changed with that revision. So our energy levels through electricity take that constant and square it in the numerator. And then the rest of the quantities, of course, have to do with the mass of the electron alone and Planck's constant. Okay, so the rest of the constants there do not care whether it's gravity or electricity. So let's take that relationship and simply replace that electrical cluster with a gravitational cluster. So it's still an attractive force, and we should have bound states. And we can do a very simple relationship by knowing that the energy levels in the hydrogen atom go as minus 13.6 eV over n squared. So if we do the ratio of that cluster of constants gravity-wise compared to electrical-wise, we could simply take our 13.6 electron volts negative over n squared and multiply it by the ratio squared. Okay, so we'll go ahead and evaluate that because it is kind of instructive to do that. So I'm going to put in all the constants in their SI units. Whoops. That should say times 10 to the minus 11. Let's not use some computer type of writing. Okay, so it's just a matter of looking up masses and the strength of gravity in newtons kilogram meter squared per kilogram squared. And this particular cluster of constants, the ratio, is a small number. It is 4.40 times 10 to the minus 40. And the units should be identical. That's the nice thing in picking that cluster of constants and having both inverse squared laws. So what this means is we can take the minus 13.6 electron volts over n squared and simply multiply it by that cluster of constants squared. Yes, and not surprisingly, it is very much smaller amount. Almost so small, I doubt if there's any way to measure energy differences of that amount, or those differences would be very long wavelength photons. Okay, and let me just check my number since this is very small numbers that can get goofed up in a calculator. Yeah, okay. And we could do something similar with the Bohr orbit radius. So let's take a look at the equation for r sub n. Of course, it goes proportional to n squared for the inverse squared law. And there's that cluster of constants again. Okay, and so gravitationally speaking, we should be able to just replace that with our gravitational placeholder. Yeah, and so the mass of the electron shows up twice. But furthermore, we can evaluate this. We know that for the Bohr atom, this is 0.0529 nanometers over, not over, times n squared. So yes, the orbit increases as n squared. And we would expect the same for our gravitationally bound atom, except the radius will be divided by that placeholder. Oh, let's write in black here. And we actually want to numerically evaluate this, so we would take the 0.0529 nanometers times the n squared, of course. That dependence is still there, but we would divide by 4.40 times 10 to the minus 40. And recalling that a nanometer is 10 to the minus 9 meter, we can convert this into meters, would be a much more reasonable approach than using our nanometers, which are too tiny for the situation. And we basically get for the R1, let's drop the n squared, 1.20 times 10 to the 29th meters. That's huge, as they say. We'd have to convert that into light years to get a better feeling for how big that is, but we will convert it into astronomical units, where 1 AU is 1.5 times 10 to the 11th meters. And based on that multiplication, yeah, that doesn't reduce the exponent appreciably. We still get a lot of astronomical units. Yeah, so the Bohr orbit for the first energy level would extend way far out in space. I'm pretty sure that's maybe even larger than the universe. but I would have to do a little bit more calculation with light years in order to figure that out.